Hi, I'm Avijit Thawani from the University of Southern California, and I'm going to be talking about representing numbers in language models. We're dealing with a very simple problem here. Language models treat numbers the same way that they treat words, which forces them to not understand that 3999 is very close to 4000 because they don't share any string characters. But we know, and we could probably encode this explicitly into language models as representation of numbers, that numbers are actually on a continuous number line. So the task that we're setting up here, the first task is of writing numbers, where we take a sentence such as the airport was 15 miles away from town. We mask the number and force the model to predict it, except instead of having a prediction of logits over the vocabulary space of the language model, such as BERT over here, we use a regression loss. And the way that we do it is we take the contextualized word embedding for mask and then convert it into a scalar value through a feed-forward network, and backpropagate using a regression loss of which is log scale, given that we already know the ground truth happens to be 15 miles in this case. Similarly, for reading numbers, what we do is we, instead of masking the number here, we mask the unit, and we pass the number into the language model not through a lookup embedding, but instead through, again, another feed-forward network that converts the number 15 into a vector representation. And then we use the same contextualized embedding for mask to classify the unit out of one of these 30 units and then backpropagate using a classification loss. The results have been promising so far. We could see that the sentence U559 had a displacement of 870 tons while submerged, where 871 happens to be the ground truth, and the prediction when you mask this by BERT, the language model, happens to be 1, the baseline language model, whereas our modification to the language model gives it a very high number, which is what we'd expect. Similarly for temperature and distance metrics as well. And the quantitative metric that we're using to evaluate our results is by what factor are the ground truths off from the predictions. So our score gets 5, which is to say, if the ground truth was 15, we on average predict somewhere between 3 to 75 miles, whereas that span is a lot larger for the baseline language model. And that's only when it's able to predict the number. Sometimes it isn't. With reading numbers, we see similar results, such that the classification accuracy, using only this control experiment, only the representation of numbers is changing, the classification accuracy jumps from 55% to 75%. And that's really it from my side. Sorry, I don't have the permission to talk about the more recent results because they're under submission, but I'll be happy to take your questions and feedback.